When I got to that scary passage on lasers, converging and diverging lenses, refraction, I wasn't scared, I wasn't worried. In fact, I even smiled a little bit because I knew that I took the time and the effort required to master this complex topic that would send other test takers inside of that room into a panic. I'm a firm believer that these types of questions are just free points. And in today's video, I'm going to teach you everything that you need to know about light and optics so you can start cashing in those free points. So without further ado, let's get straight into the video. One of the MCAT's favorite topics in optics is refraction. It sounds intimidating, but it's really just the bending of light as it passes from one material into another. Think about the classic example of a straw sitting in a glass of water. The straw appears bent, even though it isn't. And this optical illusion exists because of refraction. Refraction happens when light changes speed because it enters a different material. If the light enters at an angle, one side of the wave slows down before the other, causing the entire wave to bend and giving that disconnected straw appearance. This relationship becomes obvious when we look at the equation N equals C over V, which I have in magenta. N is the index of refraction, C is the speed of light in a vacuum, which is 3.00 times 10 to the 8th meters per second, and V is the speed of light within the material. Since N and V are inversely related, a larger refractive index means light travels more slowly through that medium. And below that equation, you really get the bread and butter of refraction, Snell's law. This equation looks more intimidating than it is. It's purely just plug and chug. The only thing you need to know is what each term means. N1 just means the index of refraction for the material. A lot of times it's going to be a vacuum or air, which is about 1.00. Sine of theta 1 just refers to the angle of incidence or the angle at which the light ray strikes relative to the normal. N2 refers to the index of refraction for the second medium, and a lot of times it's going to be water, which has a refractive index of 1.33. But of course, these are just examples. Be sure to use whatever values they give you. And finally, sine theta 2 just refers to the angle of refraction with respect to the normal. And if you're confused about the term normal, I labeled it in the diagram to the left just to make it clear. Just like in free body diagrams, the normal is simply an imaginary line drawn perpendicular to a surface. Now here's the key rule to remember. When light enters a material with a higher refractive index, it slows down and bends towards the normal. When light enters a material with a lower refractive index, it speeds up and bends away from the normal. And not only is refraction dependent on the material, but it also boils down to the light source itself. Different wavelengths of light refract by different amounts. Longer wavelengths like red bend less, while shorter wavelengths like violet bend more because violet experiences slightly higher refractive index in most materials. And this phenomenon is actually called dispersion, and it's what gives us beautiful sights like rainbows. When sunlight enters a raindrop, each wavelength bends by a slightly different amount. And as the light exits the droplet, those wavelengths separate into the individual colors of the visible spectrum. The exact same thing happens when white light passes through a glass prism, producing the familiar rainbow of colors. And so far, we've talked about what light does. It bends, slows down, and separates into different colors. But why does light behave this way in the first place? To answer that, we need to take a step back and understand what light actually is. But before we get into all of that, Let's make sure you were paying attention with a practice question. Take a couple minutes to try the practice question on your own, try to break it down and attempt it, and then we'll do it together. Okay, so hopefully you tried it out on your own. Let's get straight into the question. A physician uses a fiber optic catheter to deliver laser light during a minimally invasive procedure. The catheter consists of a glass core surrounded by a transparent coating. For the procedure to be successful, the laser light must stay within the glass core. The refractive index of the glass core is 1.5, while the refractive index of the surrounding coating is 1.2. A laser beam travels through the glass core and strikes the glass coating interface at an angle of incidence of 60 degrees. And then they give you some values which may or may not be useful. Okay, so breaking down and reading through that question, what I got was this sentence. It particularly stood out to me. For the procedure to be successful, the laser light must stay within the glass core. So when it strikes the glass coating interface, we don't want the light to refract into the coating medium. We want it to reflect at the interface and stay within the glass. This is a classic example of total internal reflection. And what is total internal reflection? Well, that is a phenomenon when you have two mediums, one of a higher index of refraction, which the light source starts in, and the second medium, a lower index of refraction. And past a certain angle, which is deemed the critical angle, all light will actually not refract into the second medium. It's actually going to reflect and stay within the first medium. And typically, the MCAT loves to use the fiber optic cable as a classic example of total internal reflection. So again, you essentially have two criteria to achieve total internal reflection. One, that the index of refraction N1 must be greater than the index of refraction for the second material, N2. So N1 greater than N2. And the second criteria is that the critical angle must be exceeded. And when that happens, let's say this is the interface, you have reflection instead of refraction. Okay, so let's look at the answer choices line by line with this framework in mind. We want to look for which achieves total internal reflection, which allows a laser beam to remain within the glass core. The light undergoes refraction because the angle of incidence is smaller than the critical angle, causing the ray to bend toward the normal. Well, while that might be true, if it underwent refraction, it wouldn't stay within the glass core. It would go into the coating medium, which allows us to eliminate answer choice A. B. The light undergoes total internal reflection. So it does include what we were initially thinking or discussing in our breakdown, but let's see what the rest of the question says to see if it's invalidated. Because it travels from a lower refractive index material into a higher refractive index material. And so we can see that B is wrong, because for total internal reflection to occur, it must always go from a higher refractive index material to a lower refractive index material. And since B has the order switched, we can eliminate it. C reads, the light undergoes total internal reflection because it travels from a higher refractive index material into a lower refractive index material and exceeds the critical angle. So yeah, it looks like C's our answer because it satisfies the two criteria that is required for total internal reflection to occur. But let's look at D and see why it is wrong and why we can eliminate it. The light undergoes reflection because the glass and coating have similar refractive indices, preventing the light from entering the coating. So yeah, if they did have similar refractive indices, this would be an effective answer, but since the question explicitly states they are different, we can go ahead and eliminate answer choice D. So now that we covered refraction, Snell's law, some of the caveats associated with refraction and dispersion, and we covered total internal reflection, I think it's best to get into a foundational conceptual knowledge of what light is, because this tends to show up quite frequently, at least throughout the UWorld banks. Alright, so what is light? It sounds like the intro to a philosophical Cars passage, but the physics section likes to keep it pretty simple. At its core, light is a form of electromagnetic radiation. The MCAT likes to think about light using two different models, as a wave and as a particle. The wave model helps us understand concepts like wavelength, frequency, and refraction, while the particle model helps us understand and quantify the energy carried by light. When we think about light as particles, we call these particles photons. Each photon carries a specific amount of energy, which we can calculate using the equation E equals hf, where E is the energy of an individual photon, h is Planck's constant, and f is the frequency of light. The key takeaway for the MCAT is that photon energy depends only on frequency. A higher frequency photon carries more energy, while a lower frequency photon carries less energy. And since wavelength and frequency are inversely related through the equation C equals F times lambda, we could also say that shorter wavelengths correspond to higher energy photons. And this is where the MCAT absolutely loves to test your understanding. They may ask what increases the energy of a light source, and the correct answer will involve either increasing frequency or decreasing wavelength. A common trap is increasing the intensity of light. For example, shining a brighter flashlight or increasing the number of photons hitting an area does increase the total amount of energy delivered, but it does not increase the energy of each individual photon, and therefore does not increase the energy of the light source itself. Remember, photon energy depends on the properties of each photon itself, not how many photons are present. So if the MCAT asks, what increases photon energy, you can have either an increase in frequency or a decrease in wavelength. But if they ask what increases intensity, you have to increase the number of photons. And you want to really do your best to keep these two concepts separate. The MCAT also likes to test the wave properties of light. So light is an electromagnetic transverse wave, meaning it can travel without a medium and consists of oscillating electric and magnetic fields perpendicular to the direction of propagation. So let's translate that into a simpler understanding. Imagine a wave moving forward across the screen to the right. The direction the wave travels is in one direction, which to the right, but the electric and magnetic fields are oscillating upwards and downwards perpendicular to that movement. That perpendicular oscillation relative to the direction the wave is traveling is what makes it a transverse wave. Whenever you have oscillation perpendicular to the direction of motion, it's labeled as a transverse wave, and light happens to be the classic MCAT example of a transverse wave. The important MCAT takeaway is that light does not need matter to travel. Unlike sound, which requires particles to vibrate and pass along energy, light can travel through empty space because it is made of oscillating electric and magnetic fields. And this is precisely why energy from the sun can travel millions of miles through the vacuum of space and reach Earth. So now that you have a good understanding of light, let's break down the three types of mirrors. Most students memorize mirror equations without ever understanding what a mirror is actually doing. If you understand one simple idea, that mirrors only change the direction of light, it will be a lot easier to understand mirrors intuitively. A mirror never creates light. It never bends light, it simply reflects it. So maybe you memorize that mirrors create a virtual image, but what does that mean? Well, notice that reflecting off the mirror, the light rays never actually meet. So if we extend them backwards, they appear to come from behind the mirror, and since no light is actually meeting there, the image is called virtual. And that's essentially all that you have for plane mirrors. They're without a doubt the simplest kind of mirrors. Now let's talk about concave mirrors. These are different because they can actually bring light rays together. So instead of reflecting light rays outward like a plane mirror, a concave mirror curves inward, causing parallel light rays to reflect and converge at a single point called the focal point. Think of a concave mirror like a satellite dish. Its curved surface takes incoming parallel rays and focuses them into one location. And this focal point exists because the mirror is changing the direction of the light rays, not because it is bending light. Remember, mirrors only reflect light. So what determines the image we see? Well, it depends on where the object is compared to the focal point. So if the object, DO, is outside of the focal point F, the reflected rays can actually meet in front of the mirror. And since light physically comes together at this point, the image is real and inverted. But if the object is inside of the focal point, the reflected rays spread apart. Our brain, similar to the plane mirror, will extend those rays backward, making it appear as if they came from behind the mirror, which creates a virtual, upright, and enlarged or magnified image. So a simple way to remember this is if the distance of the object is outside the focal point, it creates a real inverted image. If it's inside of the focal point, it creates a virtual, upright, enlarged image. And this is why concave mirrors are used for things like makeup or for shaving. When your face is close to the mirror, inside the focal point, you see a larger, upright image. And finally, I want to make a note about the sign convention for focal length, which the MCAT does expect you to know. For concave mirrors, since the focal point is in front of the mirror, on the same side as the incoming light and object, it has a positive focal length. So remember, concave mirror equals positive focal length. Convex mirrors are the opposite of concave mirrors. Instead of focusing light rays together, they spread light rays apart. A convex mirror curves outwards, so when parallel rays hit the surface, they reflect away from each other. And because the reflected rays never actually meet, we extend them backward and notice that they appear to come from behind the mirror. And since the light is not actually coming from that location, the image is virtual. Unlike concave mirrors, convex mirrors always create virtual, upright, or smaller, diminished images. The easiest way to think about a convex mirror is that it makes things look smaller and gives you a wider field of view. And this is exactly why convex mirrors are used for side view mirrors on cars. They allow drivers to see a larger area behind them, but objects appear smaller and further away than they actually are. And finally, you want to remember that convex mirrors have a negative focal length. And why is that? Well, it's because the focal length of a convex mirror is behind the mirror, on the opposite side from the incoming light rays. And since the focal point is virtual and located behind the mirror, it has a negative focal length. A negative focal length also matches what the mirror is doing physically. The rays coming off of the convex mirror are diverging instead of converging. So if you remember the ray diagram for a convex mirror, remember that the rays spread apart after reflection. They only appear to come together behind the mirror. The focal point is behind the mirror, therefore making it negative. So zooming out, the big picture is this. Plane mirrors create virtual, upright, same-size images. Concave mirrors can create real or virtual images depending on object location with respect to focal length. And convex mirrors will always create virtual, upright, smaller images. So remember, mirrors never create or bend light. They only change the direction of light through reflection. The image depends on whether those reflected rays actually meet or only appear to meet. And for the final topic of this video, we're going to be covering lenses. Unfortunately, a lot of people generally have come to the consensus that lenses are the hardest part of light and optics. But I'm going to show you that most lenses questions just require an understanding of what the lens does and remembering a few rules and knowing when to apply them. So the first type of lens we're going to talk about is a converging or convex lens. And for this type of lens, the focal length is always positive. It's always going to be positive no matter what. I want you to drill that into your head. Converging equals positive focal length value. Now, when we look at the specific ray diagram for a converging lens, we can see that the image formed is inverted. And since the light rays actually converge at this point, it forms a real image. So far we have two qualities, real and inverted. Now the magnification of the image depends on the object distance in relation to the focal length. If the object distance, DO, is more than double the focal length, then you form an image that is real, inverted, and reduced. But if you move to an object distance that is between 2 times and 1 times the focal length, so let's say the object distance is 1.5 times the focal length, all that changes is that the image is still real and inverted, but it becomes magnified. And this is the exception that you need to know for converging lenses. You can get a virtual image for converging lenses if the object distance is less than the focal length. If you have an object distance that is less than the focal length, the type of image that is produced is virtual, upright, and enlarged. So while the converging lens always produces a positive focal length, it is up to the object distance in relation to the focal point, which determines the qualities of the image produced. Now let's look at diverging or concave lenses. For these types of lenses, the focal length is always negative. And these are typically easier to work with because the image produced is always the same. It's always virtual, upright, and reduced. And we can see what that means from this ray diagram. As you can see, the image formed is on the same side where no light actually converges, so it's going to be a virtual image. And you can see that it's upright with respect to its orientation in regards to the object, and that it is significantly smaller. So that's how we get virtual, upright, and reduced. And you'll notice that I have the word diopters here. And if you're not familiar with what diopters means, all that means is it's a way of quantifying the strength of a lens. All it is the inverse of focal length. So a lens with a lower focal length is higher in diopters, and higher diopters just means it's stronger. And while we're on the topic of lenses, you might have heard people say that they have a -2 prescription or a -3 prescription. What does that negative sign mean? Well, that's actually an interesting connection. The negative sign means that they are using a diverging lens to correct their vision. And the negative sign actually refers to the focal length always being negative. So when a person has a problem focusing the light too far in front of the retina, what the common fix is to use a diverging lens to spread out the light rays and allow the light to properly hit the back of the retina. So whenever you hear someone say I have a negative or positive prescription, that just refers to the type of lens that they use, with negative referring to a diverging lens and positive referring to a converging lens. So now that we have a good foundational knowledge of lenses, let's go ahead and look at our final practice problem to tie this all together. All right, so the question reads, a researcher is designing an optical imaging system to examine transparent tissue samples. The prototype consists of a converging lens with a focal length of 20 centimeters. So already we're getting some key information. The value of f, or focal length, is positive 20 centimeters. And how did I get the positive? Well, that's because converging lenses always produce a positive focal length. The question keeps reading, during testing, a specimen is placed 60 centimeters from the lens. So now they also gave us DO, or object distance, which is 60 centimeters. And hopefully you know the most popular equation used in light and optics, which is 1 over f equals 1 over object distance equals 1 over image distance. And since we have f and DO, we could solve for image distance. So let's go ahead and plug in to get that value. Equals 1 over 60 plus 1 over di. 1/20th is equal to 3/60th. Moving the term to the left, we get 1 over di is equal to, simplifying it, 1 over 30. So image distance is 30 centimeters. Okay, and to obtain a higher resolution image, the researcher moves the specimen 10 centimeters closer to the lens while leaving the detector in its original position. Okay, so DO is now adjusted to 50 centimeters, and that has no bearing on focal length. That's an intrinsic property of the lens, so that is still going to be 20 centimeters. So now we have to solve to see where the new image is formed. So we're going to plug in those values to this same equation, and we're going to get 1 over 20. I'm just going to move this term already to that side to make it quicker. Over di, find the common denominator. 2 over 100 equals 1 over di. Di is going to be 33.3 centimeters. But you'll notice that it says the detector is fixed in its original position. It's still 30 centimeters away from the lens, but the new image forms at 33.3 centimeters. So we're probably going to get a blurry image, because essentially what we have here is, let's say that's the object, that's the lens, and this is the detector. The image is going to form right about here, 33.3 centimeters away from the lens instead of 30 centimeters for the lens. So we're going to want to look for an answer choice that reflects that the image probably gets blurry or lower in quality. So with this framework in mind, let's go ahead and let's look at the answer choices. The image remains sharply focused because the magnification increases by the same factor that the image distance decreases. Well, this is wrong on two accounts. We discussed that the detector and the new image distance don't align, so it's not going to be sharply focused. And the image distance also increased from 30 centimeters to 33.3. But let's look at magnification, because this is where it gets interesting. Hopefully you remember the formula for magnification equals negative di over do, or even hi over ho, which refers to the height of the image and height of the object. But to be honest, this is hardly used, and this is by far the more common magnification formula. And what you'll notice is that the image distance increased while the object distance decreased. And because the numerator increases and the denominator decreased, magnification does increase, but since it's wrong on the two other accounts, we can definitely eliminate answer choice A. B reads that the detector will capture an upright image because decreasing object distance changes the image from real to virtual. So I do remember discussing one condition when a converging lens would create a virtual image, and that is when the object distance is less than the focal length. And although we did decrease the object distance of 50 centimeters is still greater than the focal length of 20 centimeters, so the image is very much real. So we can eliminate answer choice B. C reads, the image becomes smaller because reducing object distance decreases magnification while increasing image distance. Well, we talked about how in answer choice A, the magnification actually increases on account that the image distance increased while the object distance in the numerator decreased. So magnification would actually increase, allowing us to eliminate answer choice C. D reads, the detector is no longer located at the image plane because the image forms further from the lens and becomes more highly magnified. Yes, D is our answer, and it satisfies the two criteria that we were talking about. One, that the image forms further than the detector, and that the image becomes more magnified. So hopefully this practice question went to show you that optics is nothing more than trying to break down the question, seeing what variables you're given, and using the right formulas to come to the correct conclusions. And that's going to conclude the entire light and optics masterclass. Hopefully, this simplified everything and all of your concerns about light and optics. I know it can be a very tricky concept, so if you have any questions, please feel free to drop them in the comment section below. See you in the next video.